Module 4. Module 4, we talk about analyze phase. Now, the analyze phase, I would like to distribute among two sections. One is the root cause management section and the relationship management section. Now, in the root cause management section, the first very important milestone that we have to cross is conducting a brainstorming session or application of a brainstorming technique. A brainstorming technique in the analyze phase talks about exploring the root causes of the problem. Now, everybody in the team now knows what is the problem that we are addressing in the process. So now the full Six Sigma team should assemble together in a meeting and share ideas, as many ideas as possible. Eventually, we can have discussion, rediscussion, filtration, refiltration to come out with the filtered and final root causes. So a brainstorming session in the analyze phase is to find out and explore root causes of the problem. Now, these root causes of the problem can be done, or the brainstorming ideally can be done in many ways. I personally would prefer the discussion, rediscussion, filtration, refiltration method. There is another method called multi-voting. Mostly, it could be applied when on any particular root cause, suppose there is no consensus within the team, then the team leader can write down all the root causes on the whiteboard. People come one after the other and tick against those root cause which they feel are important. So based on the maximum number of ticks, we will select the prioritized root causes. But before this, each and every root cause must be well understood by the people. Then only they can actually do a multi-voting. Another way of doing a prioritization of root causes is understanding the relevance and frequency of each in the organization. Accordingly, we can rate it as a high, medium, low, or 5, 4, 3. And based on the weightage, we can eventually decide which one to prioritize. Now, a brainstorming session, as I said, ideally should not be a very lengthy session, restricted to 60 to 90 minutes. Ideally, the Six Sigma project team and the sponsor also could participate. But if the green belt or black belt feels that any other person they want to call who could be instrumental and helpful for the brainstorming session, very well, that can be done as well. They can be invited as well. After the root causes of the brainstorming session are finalized and done, we resort to a very important quality analysis, which is called fishbone analysis or Ishikawa analysis or cause and effect analysis, where all the root causes we group under respective categories like person, method, equipment, environment, measurement, materials. 10 years back also, the categorization was mostly done under six M's: man, machine, method, measurement, material, and mother nature. But now the situation is changing, and every organization is resorting to a unique way of categorization of the root causes. But all the cause and effect root causes are high level root causes, like you see under person negligence and insufficient training. Why people are insufficiently trained? Why people are negligent? That has to be understood first. If that is not understood, how can we go for an improvement? So, immediately after the cause and effect analysis, we resort to another analysis, which is called the why analysis, where we keep on asking why, till that level where we find that I cannot dig any further. Your improvement will come from the granular most improvement or root cause that you have got. To give you two quick examples on why analysis. Why are you throwing sawdust on the floor? Because the floor is slippery and unsafe. Why is the floor slippery and unsafe? Because there is oil on it. Why is there oil on it? Because this machine is dripping. Why the machine is dripping? Because the oil is leaking from this coupling. Why the oil is leaking from the coupling? Because the rubber seal inside the coupling is worn out. Here we have stopped till the fifth stage, but we could have further drilled down. Why the rubber seal has worn out? This way we could have drilled down. I have mentored a Six Sigma project where I went till 14 whys. So this way you people have to go. And when you feel that, no, I cannot dig it any further, very good. Stop over there, dead end. From that granular most root cause, try to do the improvement. Then it will actually do a better improvement in the improve phase. Another example, why did the machine stop? Because the fuse blew due to an overload. Why was there an overload? Because the bearing lubrication was inadequate. Why was the lubrication inadequate? Because the lubrication pump was not working right. Why was not the lubrication pump working right? Because the pump axle was worn out. Why was the pump axle worn out? Because sludge got in. Again, we could have drilled down why sludge got in. This way, we could have drilled down further. So this is two examples of why analysis. We also, in the root cause management section, could do a Pareto analysis, which most of you could be already aware of, which is based on the 80-20 principle that to prioritize root causes, which 20% of the causes are responsible for 80% of the problems. This is mainly responsible to see which minimal causes are causing the maximum defect or problems. Let us eradicate those first. So that is for this prioritization. The next area of our discussion is on our relationship management, where we will mainly talk about three important components: hypothesis methodology, correlation analysis, and regression analysis. Now, in the hypothesis methodology, it basically talks about presumption testing. I presume that Mr. A runs faster than Mr. B. That is my presumption. It could be wrong or right. So I have to prove it with appropriate data to prove whether my presumption is correct. That is why we do a hypothesis testing. Hypothesis testing means presumption testing. I will explain the concept of hypothesis testing with with the help of few examples over here, case studies. Now, the first one, as you see, before this, I will ask you to write down as a note, which is very helpful, 6 steps of hypothesis testing. Number one, identify the null hypothesis. I will explain these steps when I work on the analysis, statistical analysis. Number one, the first step, identify the null hypothesis. Step number two, do the appropriate hypothesis testing. Number three, get the p-value. Step four, if the p-value is less than equal to 0.05, we reject the null hypothesis. Step five, if the p-value is greater than 0.05, we accept the null hypothesis. And step number six, conclusion. I think all of you have written it properly. Now let us understand this particular case study. In Illinois, there is a packing plant named Fabric Manufacturers. In it, the machine packs curtains with jars. Very good. It is supposed, that means it is presumed, that a new machine will pack faster on the average than the machine currently used. That is what we have to prove. That the pack time new is packing faster than the pack time old. That's what we have to prove. So what is the first step I have written? The first step I have written, identify the null hypothesis. Null hypothesis is nullifying what we have to prove. We have to prove that the pack time new is faster than the pack time old. My null hypothesis will be pack time new is not faster than pack time old. Then we do an appropriate hypothesis testing. Over here, there are two sets of data. So we will check for the two sets of data when it is compared on an average. We take two sample t-test. Now, the steps of doing this are very well explained over here, which I did not repeat, because we have to prove that the pack time new is faster than the pack time old. So here we have selected this option. Is the mean of pack time old is greater than mean of pack time new? As obvious. Okay. And based on all the inputs, sample one, we have selected back time old and back time new, and hypothesis testing we select from the assistant and hypothesis test menu. As because it is tested on an average between two sets of data, we select two sample t test. So what was the first step? Identify the null hypothesis. So my null hypothesis will be that the new machine does not pack faster than the old machine. Then we do the appropriate testing, that is two sample t. Then we get a p-value. What is the p-value that we have? Step number three, we got a p-value. Step number four says if the p-value is less than equal to 0.05, we reject the null hypothesis. This is less than 0.05. So we reject the null hypothesis. What was the null hypothesis? That the new machine is not packing faster than the old machine. We reject that. So what would be our conclusion? The new machine really packs faster than the old machine. This is how hypothesis testing are done. With the same data, we do another round of hypothesis testing with the same data, two sets of data, whether the standard deviation of the old machine is different from the standard deviation of the new machine. So what would be the null hypothesis? The standard deviation of the old machine is not different from the standard deviation of the old machine. We do appropriate test, that is, we select system hypothesis test, and then we select two sampled standard deviation. This way, we select the third option over here is the standard deviation of the old machine different. As simple, we get a p-value which is equal to 0.789. So it is greater than 0.05. When it is greater than 0.05, we accept the null hypothesis. What was the null hypothesis? That the standard deviation of the old machine is not different from the standard deviation of the new machine. That is what we confirm. That is what we confirm. That is our result. See, below the p-value, it is also written. The standard deviation of the old machine is not significantly different from the back-time new. That is what we decided. Another example from the earlier two were from manufacturing organizations. This one from a healthcare organization. Unique Healthcare has discovered a drug to reduce the headache. We would like to test the efficacy of this drug, so we perform a controlled study. There are 20 participants in this study. Half of them got the drug and the other half got the placebo for the first 1 month of the study period. From the next month, the first half who got the drug now got the placebo, and the other half who got the placebo earlier now got the drug. The difference in the reported times for it takes to relieve the headache and the placebo and the drug are shown in the table below. Determine if the drug is better than the placebo in relieving the headaches by at least 5 minutes. That means we have to prove that the drug is better than the placebo, right? So our null will be the drug is not better than the placebo. Here, better means reduces the headache faster. So our null is it is not better than placebo as because the data has been used here twice. You understand? There is an interchange within a month. We do a paired t-test. Otherwise, it is the same process we do. We select the first option is the mean of placebo greater than drug because we have to prove that the drug is faster. Okay. After that, we get a p-value which is equal to p less than 0.001, which is less than 0.05. So we reject the null hypothesis. The null hypothesis was the drug is not better than the placebo. So our conclusion is the drug is really better than the placebo in relieving the headache by at least 5 minutes. Whatever process we follow for a hypothesis testing, and whatever process of hypothesis testing we do, the 6 steps which I laid down, we have to follow the same. And here, as I said, we are all going through the assistant menu, selecting on hypothesis test. Then we will have 3 different panels. Now we are selecting on the middle panel where two sets of data are compared to each other. I think this is quite self-explanatory. Okay. Now, the next exercise in We All Infotech, the current process of software development results in three defects per thousand lines of code. This is from an IT organization. An improvement was made to the process, and the new process results in two defects in 800 lines of code. Can we statistically say that we have made an improvement to the process, or rather, is the new process better than the old process? So our null will be the new process is not better than the old process. Here we have a summary data. So we entered the data straightway onto Minitab and we selected the option two sample percentage defective. There are two samples of percentage defective which are compared. So based on this, whatever we have added, you can do your practice in your spare time also based on whatever is stated over here. After clicking on it, OK, we get a p-value which is greater than 0.05. That means we accept the null hypothesis. What is the null hypothesis? The null hypothesis was the new process is not better than the old process. So we conclude that the new process is not better than the old process. Another example, the number of defectives, another case study rather, number of defectives observed in a process on one of the day is 54 out of 1,000 items inspected. Can we statistically conclude that the percentage of defectives is greater than 5%? But here, in this regard, just some decimal increment would not be considered as a significant improvement. So here we are comparing one set of data, 54 out of 1,000 against a target of 5%. So we will select one sample percentage defective. One sample percentage defective as per options given on the right hand side. We get a p-value which is equal to 0.300. So what was the null hypothesis? That there is no sufficient increment. There is no sufficient improvement to the process, right? That will be your null hypothesis. There is no sufficient improvement to the process, increment to the process. So after doing the p-value, we accept the null hypothesis being greater than 0.05. So we accept the null. That means there is really no good improvement, significant improvement in the process that we say. Now, this is another example, which is called an ANOVA test. This is also from an hospital organization. Hardening of the arteries is a major contributor to ill health. It progresses by the accumulation of plaque on the interior walls of the arteries that obstructs the blood flow. This obstruction causes pressure differences within the blood flow, and eventually the artery collapses with a fatal consequences to the patients. Lifespan Pharma has built a model to investigate the collapsibility of the arteries. The research and development team has investigated three different levels of stenosis and determined the flow rates in milliliter per second when the artery collapses. Stenosis are experiments to check the flow rates of the bloods. We have to show whether there are significant difference between the three stenosis. Our null hypothesis will be there is no significant difference between the three stenosis, as because here we are using more than two sets of data on an average. We will consider on the right hand side panel, we will check with one way ANOVA. Based on this right hand side, the options that we have to select, we get a p-value which is less than 0.001. So we reject our null hypothesis. That means, what was the null hypothesis? There is no significant difference between the three stenosis. So our conclusion will be there is surely significant difference between the three stenosis. There is one example of a two-way ANOVA. The example that we just now handled was called one-way ANOVA. There was one X and of course one Y. To explain two-way ANOVA, I will explain with an example. Suppose there is a botanist who wants to explore sunlight exposure, how sunlight exposure and watering frequency affect plant growth. She plants 40 seeds and lets them grow for 2 months under different conditions for sunlight exposure and watering frequency. After 2 months, she records the heights of each plant. In this case, we have the following variables. The response variable, that is the output variable, is of course plant growth, and factors is sunlight exposure and watering frequency. So what we have to prove? Does sunlight exposure alone affects plant growth better? Or watering frequency alone affect plant growth better? Or a combination of these two affects plant growth better? So there are more than one X, and also there is an interaction effect. That is the combination factor. That's why it is called a two-way ANOVA. The next example talks about another multiple sets of data, more than two sets of data, to be honest. Riverscape Governments wants to determine whether differences in shopping behavior for men and women during normal periods, holiday period, and sale periods. A survey was conducted on how many men and women made purchases during each of these periods. This is the summary data. Okay, so there are three periods, so sets of data are more than two. So whenever between two sets of genders we select more than two options, we do actually a chi-square test for association, the last one on the right-hand side panel. So based on the selections that we have done, see it properly, number of outcomes are two, men and women, gender, X name are period, and number of X values are three because there are three periods, normal, holiday, sale. And based on all that we have inputted, we click on OK and we get a p value of 0.005. When it is 0.005, it means it is less than 0.05, so we reject the null hypothesis. Null hypothesis was we had to prove that between the two genders, the shopping behavior were there significant difference. So our null hypothesis was between the two genders, shopping behavior, there are no significant difference, so we reject that. So between the two genders, shopping behavior has been significantly different. That is the conclusion. Now, all these exercises, all this analysis, around five or six that we discuss now, are parametric hypothesis testing. Hypothesis testing are distributed into two parts. One is parametric, another is non-parametric. Parametric hypothesis testing means that the data based on which we do the testing are normal data, or the data follows a proper pattern of data. Non-parametric means either the data could be non-normal or not showing a proper pattern of data. There could be some out of pattern data. In those cases, there are two sets of hypothesis testing which we want to understand. One of American state, but the process of doing the hypothesis testing will be strictly based on those six steps which I have written. Don't follow those six steps. One of American state municipality uses two brands of paint for painting stripes on roads. A national highway official wants to know whether the durability of the two brands of paint are different or not. For each paint, the official records the number of months the paint persists on the highway, that is more durable. So we have to prove whether the durability of these two brands of paint are different or not. My null hypothesis will be the durability are not different. Then we do first a statistical analysis on the normality check to check whether these two data are normal or not. We see brand A data, which I have already explained, through statistics menu. We select basic statistics and then we check graphical summary, which shows us the normality test, where we see that brand A data, as explained earlier, is not a normal data, brand B is a normal data. So we are doing a hypothesis testing between two sets of data. One is normal, another is not normal. That's why we are going into a non-parametric data set. And the same way, after doing, we go to statistics menu. select non-parametrics, and then we select man-Whitney test. Why man-Whitney test? Whenever for a non-parametric, there are two sets of data we compare, we call it man-Whitney test. And here the p-value that we reach is 0.00, which is less than 0.05. So we reject the null hypothesis. The null hypothesis was between the two brands of data, there were no significant difference. So we reject that. That means two brands of weight are significantly different. The next analysis we do from a research organization, a nuclear power plant, nuclear scientist wants to determine whether temperature changes in the ocean near a nuclear power plant affects the growth of fish. The scientist randomly divides 25 newly hatched fish into four groups and places each group into a separate simulated ocean environment. The simulated environments are identical except for the temperature. 6 months later, the scientist measures the weights of the fish. Please conduct a Kruskal-Wallis test to prove it. Now, there are four groups where 25 fish has been distributed, and each group has a different temperature. So after 6 months, the scientist wants to take out the fish and see temperature changes, does it affect the growth of fish or not? So our null hypothesis will be temperature changes does not affect the growth of fish, right? And then we do with the 6 steps, one Kruskal-Wallis test, because there are more than 3 sets of data, because there are four groups. So that's why we do a Kruskal-Wallis test. And we have a p-value which is equal to 0.46, which is greater than 0.05. So we accept the null hypothesis. That means we conclude that really the temperature changes does not affect the growth of fish. That is all about the hypothesis testing that we discussed. Now, before I conclude hypothesis testing, in all the hypothesis testing that we have done till now, I'm not sure whether any of you have noticed, I'm showing it over here. There is always by default an alpha level of 0.05. In all, I'm going back, everywhere you will see an alpha level of 0.05. What is this? Now, whenever we talk about alpha level, I would request you to write down uh, 4 points. Please write down. Number one. The opposite of null hypothesis in hypothesis testing is called alternate hypothesis, which is marked as HA. Null hypothesis is represented as HO. Point number two, if the reality is null, if the reality is null but proven not null, it is a type 1 error or an alpha error. Point number three, if the reality is not null but proven null, it is a case of type 2 error or a beta error. Now let me explain this with a very famous example globally. Suppose there is a person who, okay, first discuss the point number one. Alternate hypothesis is a term in hypothesis testing, which I will tell you, just learn it and forget it. Alternate hypothesis is just the opposite of null. When I say I accept null hypothesis, that means I reject alternate hypothesis. When I say I reject null hypothesis, that means I accept alternate hypothesis. But I never discussed alternate hypothesis earlier. It is only for you people to know that there is a term which is called alternate hypothesis. The second point says if the reality is null, etc., etc. To explain this, I will go through an example very commonly used globally. That there is a person who has been caught for murder and he has been placed to the court. Now, in the court, till this person is proven guilty, he is innocent like all other persons. Now, the reality is that we will treat his innocence as null and guilty as not null. Okay, his lawyer will always try to prove that he is innocent. His opponent lawyer will always try to prove that he is guilty. So the point was if the reality is null and it is proved not null, that means the reality is he is innocent. I told you null means innocent. The reality is he is innocent, but proved that he is guilty. That is the biggest mistake in the judgment. That is called a type 1 error or an alpha error. Now, always you see in an hypothesis testing, there is always an alpha level or alpha error provision for 0.05, that is 5%, because a hypothesis testing we always do with 95% confidence. That's why a provision of 5% always is kept over there. Okay, that means whatever be our decision, there could be by default 5% error possibility maximum. It can be. Okay, so we keep a provision statistic. The second option says if the reality is not null but proven null, it's a type 2 error or a beta error. Now, the type 1 error, which I said alpha error or type 1 error, that is the biggest mistake because in that case, an innocent person, you are killing that person, hanging him till death. But in the second case, the reality is not null. That means he is actually guilty, but proven innocent. He's set free. It is also a problem in the judgment. It is also a wrong judgment, but it is not so dangerous that you are not killing an innocent person. So it is called a beta error or a type 2 error. Next discussion we will have about correlation analysis. Correlation analysis indicates between two sets of data if there is a mutual or correlationship that exists between two sets of data. There can be three results: strong positive correlation, one data increases, other data increases; strong negative correlation, one data increases, other data decreases; and no correlation. Positive correlation is indicated with the value 1 in on Minitab. Negative correlation as a -1 and 0 indicates no correlation. This correlation analysis could be plotted with a diagram called scatter diagram, where you see for positive and negative correlation, there is a pattern of data, but for no correlation, it is a true scatter. One case study, if I want to check if TV installation time is having a correlation with TV order processing time, it means we want to check a correlation whether TV installation time is having a relation with TV order processing time and vice versa. So we select statistics menu, go to basic statistics, select correlation, and based on the process steps as shown on the right hand side, we select the variables installation time and order processing time. Click on OK. We get a correlation value of 0.426, which is slightly more than 0. So it is ideally a scatter diagram or no correlation. Even if you say this is a positive correlation, but it's a very weak correlation because it is not one. It is not one. Regression analysis talks about how much the Y data is dependent on the X data, or how much the changes to the X data is having an impact on the Y data. Okay. In regression equation, there are two values we generally check. One is the p-value, which should be greater than equal, less than equal to 0.05, and then R-square value, which ideally should be greater than equal to 90%. That is how much percentage of the data are having a good regression. So this is one case study on regression. The manager of Princess Motors wants to investigate how the plant's electricity depends on the plant's production. So here, plant's electricity usage is the Y data because it is dependent on the car production, plant's production. So plant production or car production is the X and electricity usage is the Y. Based on this, we go to assistant menu, select regression, and as because there is only one X, we select the simple regression. Y column is, of course, electricity usage. X is, of course, car production. And whenever we check one-to-one relation or regression, we select the linear regression. We select the linear regression. Click on OK. We get a p-value of less than 0.001, which is less than 0.05. So when it is less than 0.05, we say that there is a good regression between electricity usage and car production. But the R square value, instead of 90%, it is only 80.21%. So that's a decision which has to be taken by the organization whether we will go with this or not. But in energy sector, I have seen even if the R square value is greater than equal to 75% and above, they take it. So it's an organization's decision. Regression, another example. Lucky Foods is analyzing factors that affect the percentage of crumbled potato chips per container before shipping. If you are conducting the regression analysis and include the percentage of potato relative to the cooking temperature as your two predictors, we are producing crumbled potato chips and we have two predictors, that is two excess, two inputs, percentage of potato, that is the quantity of the potato, and the cooking temperature. So there are two excess. Whenever we have more than one axis checking, it is called a multiple linear regression. In the earlier example, we did a simple linear regression because x was 1. Here there are multiple x's, more than one x. We are doing a multiple linear regression. There is an advanced regression which is called, so till now we discussed about linear regression, simple and multiple linear regression. There is another regression which is called a logistic regression. Logistic regression and linear regression, the difference between them is, in case of a linear regression, the output is always continuous. In case of logistic regression, the output is always discrete. There are three forms of logistic regression: binary, ordinal, and nominal. What is a binary logistic regression? I will explain with an example. A medical researcher wants to examine the relationship between the age that a patient suffers a myocardial infarction and whether the patient has a favorable or an unfavorable outcome after treatment. So don't you feel it is binary? Because the response is a binary variable and there is only one predictor, the researcher uses a simple binary logistic regression. The next one is ordinal logistic regression. Ordinal logistic regression that have an order. In order, it will appear as an output. A field biologist studies the survival time of salamanders and wants to determine whether survival is related to region and the level of water toxicity. The biologist divides survival time into three categories: less than 15, 16 to 30, and over 30. Don't you feel it's in a proper order? So that's why it is called ordinal logistic regression. Nominal logistic regression is almost similar to uh, ordinal logistic regression, but only difference is it does not have an order. A school administrator wants to investigate the variables that affect a student's preference for certain classes. It can happen at random. The administrator uses nominal logistic regression to determine whether a student's age and the teaching method for a class is related to class preference. So it can happen any class preference. There is no proper order. That's why it is called a nominal logistic regression. One example of a advanced regression, logistic regression, a marketing consultant for a revived popcorn company investigates the effectiveness of a TV advertisement for a new popcorn product. The consultant shows the advertisement in a specific community for 1 week. Then what the consultant does, he randomly samples adults as they leave a local supermarket to ask whether they saw the advertisement, yes or no, and whether they bought the popcorn, yes or no. The consultant also asks adults what is their annual household income. Because the response is a binary, the consultant uses a binary logistic regression to determine how the advertisement and income are related to whether or not adults sampled bought the popcorn. View add yes or no, that is already there. Every customer is replying whether I have seen the ad, yes or no. And the bot is, if bot, they are marking it as one. If not bot, it is marking as zero. So in both the cases, these are binary examples because it is coming in only two forms. So that's why they have done a binary logistic regression. At this stage, your process, you have clearly understood what is the root causes of the problem, and you also know how your process you finally have to improve, how much you have to improve, not how, but how much you have to improve, so that you can attain the CTQ or the specification limits given by the customer. So that will help you to create a gap analysis now, that what we need to attend and where are we now. That is the gap you have to fill up. And accordingly, you'll be working on this. With this, we come to a close of module 4. Further discussions we will have in module 5. Thank you.